Last time we learned how the Fourier series builds signals out of repeating sinusoids. If you missed that video or any in this series on fixing your FFT, you can find the whole playlist by clicking on the info card up there in the corner. But most of the useful signals we deal with from day to day don't repeat themselves. For that, we need the Fourier Transform. But the Fourier Transform also builds its signals out of repeating sinusoids. Is it possible to build a non-repeating signal out of repeating sinusoids? Let's take a simple sinusoid with a frequency of 500 Hz, like this one. Now, let's take another sinusoid with a frequency of 501 Hz. You can't hear much difference in pitch, as our ears are not sensitive to such small changes in frequency. However, when I add the two sinusoids together, listen to what happens. They interfere with each other. Sometimes they are in phase and add to each other, and the interference is constructive, and sometimes they are out of phase and cancel each other out with destructive interference, making this sort of beating sound. This happens once per second, as the difference in frequency between the two sinusoids is 1 Hz, so we say the beat frequency is 1 Hz. Okay, so let's get rid of the 501 Hz sinusoid and replace it with a 500.5 Hz sinusoid. The beat has slowed to once every 2 seconds. The period of this signal is now 2 seconds. If we replace the 500.5 Hz sinusoid with a 500.25 Hz one, the period of the signal now extends to 4 seconds. In short, the closer two consecutive sinusoids are in frequency, the longer they will take to cancel out. This is implicit in the n over p frequency term of the Fourier series. N is the index of the frequency term, and p is the period. The greater p is, the smaller the jump between one frequency n over p and the next n plus 1 over p. Now let's consider the nature of a non-repeating signal. What's its period? Well, it doesn't have one, does it? It doesn't repeat, so there's no period to measure. But hang on a second. As the period p gets larger, the signal takes longer to repeat. What would happen if p was infinitely large? The signal would take forever to repeat. Therefore, we could think of a non-repeating signal as a repeating signal, just with a period p equal to infinity. Using the same logic, what happens to the frequency components of a non-repeating signal, a signal whose period is infinite? As the period gets larger, the frequency components move closer and closer together, until they are so close that the jump between one frequency and the next is infinitesimally small. Therefore, if we add together a 500 Hz sinusoid and a 500 plus some infinitesimally small bit of a Hertz sinusoid, we can create a signal that would fade in slowly at the beginning of time, reach a peak at time equals 0, and fade out again by the end of time. We have just made a non-repeating signal out of two repeating sinusoids. But even though this signal doesn't repeat itself, it still lasts for a very long time. It lasts forever. Normal signals are silent for a lot longer than this signal here. How can we generate that silence? If two sinusoids infinitely close together in frequency can interfere destructively and cancel each other out at the beginning and end of time, maybe adding more sinusoids could produce more silence. Because our time together is limited, for the next demonstration, I want us to imagine that forever is only 2 seconds long. This means that the closest two frequencies can be together in a signal is 0.5 Hz. We saw before that if we add a 500 Hz sinusoid to a 500.5 Hz sinusoid, we get a signal that takes 2 seconds to fade in and fade out again. Let's add a third sinusoid at 499.5 Hz, set its amplitude to 0.5, and reduce the amplitude of the 500.5 Hz sinusoid to 0.5 as well. Can you hear the signal getting slightly shorter? there's a little more silence at the edges of the signal. Maybe if we add some more sinusoids, we can generate even more silence. I'm going to add in 2 more sinusoids at 499 Hz and 501 Hz. Set their amplitudes to 0.6 and raise the amplitude of the 499.5 Hz and 500.5 Hz sinusoids to 0.9. The signal is definitely getting shorter, but there's this noise on either side of the signal. So we need even more sinusoids to cancel out the noise. If we add enough sinusoids at just the right amplitudes, listen to what happens. The 500 Hz sinusoid is the biggest sinusoid in this signal, but we need additional sinusoids at adjacent frequencies to fade the 500 Hz sinusoid in and out. However, as we add in more sinusoids to interfere destructively with the main frequency, they themselves add to the beginning and end of the signal. So we need even more sinusoids at adjacent frequencies to cause even more destructive interference and cancel them out too. This signal is now silent for a good portion of what I called forever. We have managed to make a short, non-repeating signal by adding together repeating sinusoids. If we look at what we've done in the frequency domain, we can see the magnitudes and frequencies of each of the sinusoids we used to make up the signal. Of course, 2 seconds is not forever, and if I extend the time domain graph beyond the initial 2-second period, we'll see the signal repeat, because the distance between adjacent frequencies was 0.5 Hz. However, if we were to reduce the jump between frequencies until it was infinitesimally small, this signal would never repeat itself. How can we use what we have just learned to turn the equation that calculates the frequency components an and bn of the Fourier series into something that can cope with non-repeating signals?